Radit, could you hear me chomping on my gum? I did that for you. Let's talk real fast. Would you say this graph, is continuous? Oh my goodness, right there. Continuous. Yeah. Daria, you agree this graph is continuous? Let's say that this is 5. What do we want to say this is? 3. Okay, I'm just going to switch it up a little bit. Okay, this graph is continuous because, what is f of 5?
3.
What's my limit as x approaches 5?
3.
Because my limit, as we approach that, equals the value of the function, we know that it's continuous, right?
C.
Okay, what if I change the picture and it was like this? Oop. Is this continuous? No. Why? What's f of 5? F of 5 does not exist. What's my limit as x approaches 5?
3.
Still 3. Do these equal?
No.
Does not exist equal my limit? No. That's why it's discontinuous. Removable or non-removable? Removable. It's a whole. Word? Okay. Hold on. What about this one? F of 5, we're going to say that's 3, and this is 2. Curious, what's f of 5?
3.
What is my limit as x approaches 5? Is this one continuous?
No.
Discontinuous because, yeah, there's a jump discontinuity. My limit does not equal the value of my function. Cool? Great. So now knowing this, we're all on page 17. Colin's age, Sophia's age, Graham's age. It was just brought to my attention that I don't know how to number a number line. Yeah.
Wait, that's okay. Numbers on.
Thank you for letting me know. We're going to just act like that didn't happen. But unfortunately, now it's recorded on film forever. No problem. Sorry, Braddock. Now it says, hey, we've got this function and this function going on. It says, I know that the limit exists. I know that the limit exists as x approaches 4. 4 is where we have a potential break, but they're saying, as I approach 4 from the left and from the right, my limit exists. Word. And it's continuous. Therefore, f of 4 is going to be the same thing as the limit. Find the value of k. How are we going to do that? If I'm saying I know the limit exists on the left and the right of 4, what do we have to do with both those equations? Thank you, Mr. Greer. He says set them equal, right? Let's go say x squared minus k. It's got to equal negative 3x plus 18. Where is the only spot that we could be having a potential break? Is at this 4. You guys, this will always be the value that we plug in for continuity every single time. That number will always match, and you'll always plug that in for the x values. Word? Plug it in. We got 4 squared is
16
minus
k
equals
negative 12
plus
18.
word. Go find k. So we feel good about k is 10. That makes it continuous and my limit exists. Check this one out. It says, all right, we've got this function that could have a potential break at 5. For what value of k is it continuous? For something to be continuous, as I approach 5 from both sides, you with me, Healed? It's got to be the same. We got to take what and do what? Set them equal to each other. And where is my potential break? At 5. So you guys, when you write this, you can just plug in 5 for your x value. Look at those answers. AP will never expect you to get those decimals without a calculator. So you guys, we're going to go to our calculator. How would I use my calculator to help me on this?
Guess and check.
Oh. See if they're equal. How would I do that? What screen are we looking at? But I've got variables in them. I've got a k and a k.
Common denominator.
Let your calculator do the work.
Plug in the answers in for k, your options.
Well, okay, that's a lot of guess and check. What if I graphed this equation? Yeah, what if I graph it? You guys put this guy in for your y1. Put this guy in for your y2. You guys were curious if they intersect. That's where they're going to be equal. So you guys, we're all going to go type in my 12 over x cubed plus 5 And then that's my y1. Then my y2, I'm going to type in x squared minus 5. I'm going to do a little zoom 6. Whoa, look at my computer. So we've got a crazy graph going on. And what I want you guys to do is you're going to hit second, trace. Option 5 is intersect. Second, trace 5. Then it's going to say first curve, second curve. All I want you to do is move your little cursors towards where they're intersecting and hit enter 3 times. Move your little cursor close to the intersection, hit enter, enter, enter. What did you get for that X value?
2.2.
Nice, guys, that's it. That's where they intersected. At X is 2.377. Here we go. Hey, F is a function. Defined above, I put it below for the sake of space. For what function makes it continuous at 3? Set them equal to each other. Where am I putting that 3? You know it. Boop. Set them equal to each other. We got a squared plus 9 equals a times. Beautiful. I haven't seen one quite like that yet.
You divide by a and cancel out.
No, because we got an a squared. Not everything has an a. A squared, Daria's on it. Minus 6a plus 9 is 0. We got to factor it. We got to factor. We add 2. Multiplies to be 9. Adds to be negative 6. Daria, you said it. Negative 3 times negative 3 multiplies to be 9. Adds to be negative 6. Therefore, A is, boom, 3 only. That's right, Sammy. Here we go. Let's take a peek at this one.
C.
He says C is not C. Oh, but what are you doing?
0.
Gosh, listen to Greer. He's saying if I plug in a 0 here, we're going to have 0 over 0, which is no bueno. We got to do something, right?
Yeah.
So this is like Daria's favorite thing. She knows this. You know the sign of 3x over 3x as x approaches 0. What's that identity? That equals 1. But is that what I have right here? What do I need to multiply that by? Yeah, you agree? Times 1/2 keeps me what I started with. Equals C. We're still setting these equal to each other, but we did have to manipulate this a little bit. Exactly, because we know this limit as sine of 3x over 3x, that's just going to get me 1 times the half gets me C. Boom. When we get 0 over 0, by plugging that in, you can't just say 0 or undefined because it's not either of those. We got to just do some more with it. He says just set them equal. I agree. Where are we setting them equal? What am I plugging in for x?
-1.
Yeah, make sure you're plugging in that -1 and for your x's. So we're going to type 4 minus cosine of -1 in for y1. C plus 5 ln of -1 plus c in for y2. Second, trace intersect. Move your cursor close to the intersection. Enter, enter, enter. All right, I got 2.269. So unfortunately on your paper, these graphs were terrible. So we're going to just go through one at a time and I'll show you what to graph. If I were you, I would put a dotted line here. We're going to call that C. That's my vertical asymptote. And my graph is going like this. Boo! This is the parts that if I were you, I would outline. Okay, guys, so we got this little graph drawn, okay? Just focusing on the first one. I'll fill you in on the others. As I approach C from the negative side, what would you say?
Infinity.
Infinity or does not exist. We're going to work through some things that are talking about infinity. So I'm good with you writing either. I'm truly, they're both right, Colin. But the questions that you'll see later are as x approach, it's asking about infinity. So just being familiar with both. That's all I ask. How about as we approach C from the positive side? Also infinity. What would you say that limit's going to be then? Does not exist or infinity. But I'm good with either. Okay, but just being familiar that they're both okay. Cool. So what about over here? This graph, if I were you, I would draw a vertical asymptote there, and I'm going to say C. I'm also going to say my graph is doing this.
What's disgusting?
What happens as x approaches c from the negative side on this one? Negative infinity or does not exist. How about from the right-hand side? Infinity or does not exist. From both sides? Definitely doesn't exist. Let's take a peek at this one, you guys. You know what my graph is doing. I got a vertical asymptote here.
Negative infinity.
Yeah. From the left and the right sides, we're going to negative infinity. What about my final limit? Yeah. Or?
Negative.
Good. This one's a little funky. What you guys can't see is that this point is C, comma, L. We have a vertical asymptote there. And the graph is doing this. So as I'm approaching C from the left side, as I'm approaching C from the right side, therefore my limit, agreed. The big takeaway of these four pictures that did not print nicely at all. When there is a vertical asymptote, what is my limit every time? Does not exist. We're involving infinities anytime there's a vertical asymptote. Deal? So, what if I ask you questions like this guy?
Yeah, that's
When I plug in a 4, what do we have going on?
Vertical asymptote.
I've got a vertical asymptote, don't I? Isn't that important to know? Is this 0 over 0? No. This is 5 over 0, so this is like a kind of new ball game. Do you agree we have a vertical asymptote at 4? If I were to let you see what this graph looks like, we got a vertical asymptote as x approaches 4. I'm sorry, at 4, so it looks like this. Boop and boop, right?
Yeah.
Okay. So, what are we going to say my limit is there?
Does not exist.
Yeah, so you're saying, all right, my limit does not exist. You guys, do you want to write yourself maybe a little reminder? How did I know I had a vertical asymptote there? The denominator is 0 at 4. The denom. What if we're given a question like the one to the right of it? What's going on at 2? We still have a vertical asymptote at 2 because that's when this denominator equals 0, right? They want a little bit more specific. They're like, what happens as x approaches 2 from the positive side? You're like, okay, I know I've got a vertical asymptote at 2. What's going on from the positive side of it? Let me show you. So if I've got negative 7 over x minus 2, and then we add 5 to that. That's just shifting it up. My graph is looking a little, and again, you can draw this if you want, you don't have to. As x approaches 2, my graph is looking like this. And it's saying what happens as x approaches 2 from the positive side? Negative infinity or does not exist. What if their answer was negative infinity as opposed to does not exist? Like, how would we know without a calc that it's negative infinity? You know what I'm saying? This is what I want to teach you. If they're asking from the positive side, we know there's a vertical asymptote there, right? We know. So my answer is either going to be negative infinity or does not exist, right? We know it's got to be n infinity. What's the number that's to the positive side of 2? As we're approaching 2, though, get a little closer. 2.1, right? Guys, all you have to do is we're going to say, all right, I'm going to go think about as x approaches 2 from the positive side of negative 7 over x minus 2 plus 5. If I were you, I'd plug that little 2.1 in right there. I'm doing a little 2.1 in by hand because I'm just looking from that right side. Guys, I do not care what the value is. I already know it's going to be n infinity since I've got a vertical asymptote. I just want to know if it's going up or down. So we just have to get the sign of this. Is this positive or negative? 2.1 minus 2 on the bottom. Positive or negative? Positive. A negative over a positive is? Negative. So negative 7 something blah, blah, blah. Plus 5 is still going to be negative, okay? So because this got us a negative value, that's how we know it's going to be negative infinity. Yes, 100%. But I'm just saying if this was a multiple choice and their answer was either negative infinity, 5, or 2, and D&E wasn't an option, I just want you to be able to sleuth how to get negative infinity versus positive. Let me say it one more time. You're going to just pick a number close to it. You're going to plug that number in, and you're just going to see if the value is positive or negative. That dictates the positive or negative infinity. Okay, let's do the same thing on this little ditty. 1 over x. You're like, I can't quite remember what that graph looks like. You with me, Daria? 1 over x, I'm not quite sure what the graph looks like. If I'm looking from the positive side, let's go plug in, what, 0.1? Oh, wait, first, before we even do that, if I plugged in my 0, I'm going to get 1 over 0. What's going on at 0? We got a vertical asymptote at x is 0. You guys agree with that? Vertical asymptote at x is 0 because that's when my denominator equals 0. So at a vertical asymptote, I'm either going to be going to negative infinity or positive infinity, and I got to figure out which one. So now I'm going to plug in that number really close to 0 on the positive side of it. What would 1 divided by a 0.1 be, positive or negative? Positive. Because of that positivity, boom, I know we're going to positive infinity or does not exist. But if it was multiple choice and does not exist was an option, that's how we get positive. You okay with that? What do you think would happen if, let's actually ask to the left. Hey, Beamer. As I look at 0 from the negative side, what number might I plug in? Negative 0.1. What's 1 divided by a negative? It's a negative. How did I know we're talking about infinity? Because we have a vertical asymptote at 0. Any limit as I approach a vertical asymptote will be positive or negative infinity. Let's just take a peek at this graph real fast. 1 over x. Anyone make any predictions? I like it. We knew from the right-hand side we were going to positive infinity. From the left-hand side we were going to negative infinity. Therefore, at 0, it don't exist. And our graph looks like that. Here we go. 1 over x squared. Where's my vertical asymptote? What happens when I plug in a 0 here? 0. Yeah, vertical asymptote at x is 0. So I know we're talking infinity or negative infinity. I know it. If x is 0.1,
it's only going to be positive.
It's only going to be positive. Interesting. So you're saying 0.1 squared is positive? Yeah, okay. So we're saying it's going to be positive infinity because 1 over a positive will be positive. So you're saying from the right-hand side of 0, we're going positive. What about from the left-hand side? Give me a number as we approach 0 from the left. Negative 0.1, square it. And it's going to be positive. 1 over a positive is positive. So from the left-hand side, we're also going to positive infinity. I know it's an infinity because we have a vertical asymptote there. What would you say my limit as x approaches 0 is? Infinity or? Very good. Let's picture this in a table, in a table, hosier. Here we go. We basically need to match this phrase with a table. As x approaches negative 6, my limit has to go to negative infinity. Do my x's all look like they're approaching negative 6? Yes. My x's look good, don't they? My y's have to approach negative infinity. She's saying it's not D. These are going up real high. C, one's going up and one's going down. B, one's going down and one's going up. A, they're both approaching a real big negative number. Down with A? This is a good picture thinking one where a function is continuous. We don't have any holes. Ooh, except at x is 9. It says at 9, or as x approaches 9, my limit is negative infinity. There's going to be a what kind of asymptote? A vertical asymptote. If I approach 9 and I'm going to negative infinity, you're saying there has to be a vertical asymptote there. I love it. What's the equation of a vertical asymptote? X or Y? Vux. Vertical is x equals. You feeling D? Last one. I have no idea who it was, but maybe sad. Here we go. Can you translate these words to some calculus symbols? You guys, what does arbitrarily large mean? Infinity. Arbitrary because infinity is not an actual number. X is getting sufficiently close to 2. How do I show that with calculus? Yeah, my x is approaching 2. And my limit's approaching infinity. C it is. So we are done. Here's what I'm going to ask. In your homework packet, you're going to do problems from 113 and 114. I believe those start on page 11 and finish on 13. Please do 11 through 13. Guys, doing those and not checking with my key, is that good at all? No. Not helpful at all. As you do those, I am going to grade and show you all your grades for all your classes. Sound good?